Hello, I'm Beth Carey, the CEO and co-founder of Pat Inc. And welcome to our new series, The Next Generation AI. We'd love you to subscribe if you haven't already, so that you can be notified of these episodes in this series and hopefully interact with us on live stream. But of course, it's available later as a recording. So this is part 2 of the episodes on the scientific crisis. And you might be thinking, what's the scientific crisis? What do you mean? Let me give you the business context. In the last week, Meta, previously known as Facebook, released their large language model called Galactica. It was trained on 48 million scientific papers, but it was withdrawn from their demo for the world 3 days later. And the question is, why was it withdrawn? In that period, there was a lot of interaction on social media by scientists concerned about the misinformation that was being generated by this large language model. And as you can see, people were saying, or scientists were saying, why is it generating misinformation? So that's some of the background for this episode today. John Ball talks about what we call the scientific crisis, and you'll get a bit of an understanding what that means and why we're seeing these sorts of behaviours from technology today. So I'll hand over now to founder, cognitive scientist, John Ball. Thanks, John.
Thank you, Beth. Great to be here, guys. Nice to see you again. I'm John Ball, the CTO and founder of Pat Inc. And what we did last time was we worked through what it was that took us from the 1930s to the 1990s, where the parsing technology for NLU, NLU is not going to work if you can't recognize sentences. The parsing technology was never effective. And the reason it wasn't effective was, firstly, the model that it's built on with parts of speech is highly ambiguous. And then secondly, the fundamentals of a language-based system where you take information, convert it into this parse model. Once you have that parse model, the theory should be this is now part of your language, but you can then generate invalid syntactic models from that syntactic model. So if the system's not bidirectional, it's never going to work. So that's what we got to in the 1990s in the last few. Now what we're going to do is look at how computational models from the 1990s took over, leading to today's models where we now use word vectors as a representation of meaning. And I say meaning in quotes because it's not meaning. And then those systems are used to solve all sorts of things. So the large language models is an implementation of that. But the inaccuracy of those word vectors is without meaning is then leading to systems that still don't work. And worse, because they've got these incredibly large memories, are able to generate things that look like they're working when in fact it has no idea what it's saying. It's just making stuff up. So part 2, we're just going to look at how the systems keep working without meaning, and deep learning and machine learning is integral to that. Okay, so let's get rid of that. So today's overview is in these 3 parts. So why does NLU suck? It's because it's not including meaning, but we'll go into a bit more detail than that. Distributional semantics is the underpinning science that enabled people to say word vectors are a good way to go. But the science doesn't stack up. That's not what anybody has said outside of behaviorists who are basically saying you can't work with meaning. And then we're going to look at a very big investment from Stanford University, where they're throwing a lot of money into backing up these deep learning foundation models. So if we think about what the history was, Noam Chomsky came out with a great model. It was called a revolution, and then we were stuck being unable to pivot that scientific model for the next 30 years. And now in the next 30 years, we're stuck with this concept where deep learning looks like it's going to be the only model that we can consider. And that's not the right way to progress the science. We need to bring the meaning in. We need to incorporate context, which is what linguists have been telling us now for many decades, including in the 1950s. So let me show you what my references are today. There's this book. So I'm not saying go out and buy these computational linguistics books, but that's one of my tasks as a scientist, to work out what it is people are saying. So this is a good one because it's from 2013, and it explains how, if you're a computational linguist, you basically use the 1950s, 1960s Chomsky model, the formal model of linguistics, in order to do your work. So basically, work without meaning continues with these computational linguistics models that then morphed into the deep learning models. And then this other book, which I think is probably the Bible for AI. This is the Russell and Norvig book. So these guys are very strong into, you can do a lot with data. And I'll take you through what their analysis was from the mid-'80s that has led us to the position that we're in today. And it's interesting because if you can understand what the expectations were that haven't come off, we can then work out how to pivot to something that will work. Now, where's that other screen gone? There we go. Okay, so the science of NLU sucks, partly because we've been going at this for a long time. I think we've lost the view of what we're trying to achieve, which is, I want to interact with machines naturally. I want to talk to my phone and have it respond to me in normal English, because I'm speaking English, but in any language that I happen to be speaking. I want that interaction to be working. And I want that to apply to all my computing interactions and so forth. The behaviorist model that we've started all of this with hasn't worked. And as I said, that's what we talked about last time. The other thing that's a bit annoying is when we talk about NLU, one of the presentations that you can see Chris Manning from Stanford University, in fact, he pivots from this idea, and he's a linguist, he pivots from this idea that Stanford's going to teach you about all of these great technologies, NLP, natural language processing, and it's going to include NLU, yay! And the problem is that the NLU that they're going to teach you isn't language understanding. It's simply taking a bunch of word vectors, adding those vectors together, and then matching it to some sort of intent-based model. So you're basically not doing NLU, but you're badging it NLU so people think they're being taught what language understanding is about. And the trouble is, until your science is mature, if you simply keep teaching and misusing the words, you're not able to then get the next generation of students to go, oh yeah, but we know this doesn't work and that doesn't work. So people today probably think that conversational AI is the best thing that we can ever do because it's based on NLU, and it doesn't work. And the reason it doesn't work is because it's not based on understanding. I'll give you a demo after we go through the science to show you what NLU looks like, what context looks like when you're applying it to actual human language. Okay, so how does science work? Quick review here, guys. Well, you look at what works. So you build your model, you look at what works, you refine and look at what doesn't work, and then you start iterating. And if you can make a better version because you've changed your model, great. That model looks like it's good. If it makes it worse, then look at your model again and keep changing it. So that sort of iteration over science is a very effective one. And it's not the one that we've been pursuing, as I'm going to show you over probably the next 10 minutes. So think about it. Noam Chomsky came out with a formal model in 1957, and we iterated on that thing how many times until 1990? Well, Chomsky changed his model once or twice, but the concept of the formal model has not left. It's still current. So we're working off 1950s concepts today, and we've not iterated that model, not in the NLU, NLP field. And that's a problem. So what we want to do is look at how we can iterate the scientific model. So I'm going to Norvig's book now, so Russell and Norvig's book. Their argument is that in 1987 we made AI scientific, and there's guys that can deliver jokes, but not. So they made it scientific. It wasn't scientific. What they did was they put this engineering facade over the top of it and forced everybody to follow an experiment model, but that's not how science works. We'll go into that in a bit. But so their claim was that AI became scientific in the mid-'80s, and I claim that in the 1990s, what we saw was that computational linguistics was better than other types of linguistics where you were working with well, parsers and parts of speech and so forth. But those computational linguistics models were working against these new benchmarks that were set to deal with a scientific challenge. We got lots of data with the internet revolution in 2001, and then deep learning got its 10% improvement with Geoffrey Hinton's team with ImageNet. They got a 10% improvement, and as a result of that, we basically seen everybody switch over to deep learning to solve everything. And unfortunately, it solves a lot of problems. It doesn't solve NLU. So why doesn't it? Well, if we look at this model here, you can see that if we have phrases, the things that comprise language when you're speaking in words, whatever language you speak. And those are signs. Those are either symbols, so they connect to some preconceived meaning that we all accept, cultural type thing, anthropology, or they're an index where it links to something that indicates something else. The example of an index is you see smoke, you can then decide that there's fire there because the index for fire is smoke. And in language, we see lots of indexes like pronouns, I, you, he, she, it, they, and we see it in temporal examples like now, later. You're referring to the time now, but if you want to make that something concrete, you have to do one more step. It's an index. And so all of today's models are focused on signs. And when all you have is a sign without meaning, you're pretty much stuck with statistics or some sort of pattern. So here we can see automatic speech recognition. It's looking at phoneme patterns, phone patterns, sequences, translation, machine translation, large language models. All of these things are working off the signs. Why? Because there is no meaning. We're not even researching how you would put meaning into these models. Okay, so let's just jump out of this for the moment and have a look at what happened to the science. I don't know Mark Lieberman, but there was this guy, John Hutchins, who died a few years ago. He was an amazing guy at machine learning and not machine. Okay, dogs barking. My head stops working. He was this expert in machine translation, and on his website, he just had hundreds and hundreds of presentations, and he was recommending various presentations that were quite valuable to tell us about the history. And apparently Hutchins' work will be back online at some point. But anyway, he pointed me to this example, and this is why we've had some problems with AI, and this is where the AI winters come from. So this guy called John Pierce was a Bell Labs executive, was involved in transistors. There's the guy, looks like a pretty happy guy. And the two big projects that he oversaw was the LPAC report, which was around machine translation. So as you can see, they're 1966. And then he wrote this Wither speech recognition paper in 1969 where he was critiquing speech recognition. And his point was that until the science is ready, don't start spending millions and millions of dollars on projects where they're not scientific. You're just saying, I'm going to do this. You burn through, probably back in those days, $1 million, these days, $10-20 million, and you get nothing from it, not even data that you can use to produce some other improved model. And in the LPAC report, so this is 19, and here, what the total annual expenditure for R&D. So what should it be? The bottom line was the committee said, if you can take all that money that you're wasting on machine translation and simply get some translators to translate the key things, maybe you can do some sort of tool set that helps with machine translation. That's a much better use of public funds. If we keep going here, I think nope. And then the Wither speech, this is probably the more famous, where John Pierce really takes the gloves off and bashes people around the head a bit. It's still valid today. So he says a general phonetic typewriter is simply impossible unless the typewriter has an intelligence and a knowledge of language comparable to those of a native speaker of English. And when you think of it, if you're hearing something, I've got examples in some of my Medium articles where I said I'm on Wallamatta Road, and the system doesn't know Wallamatta, or maybe it does, but it's low probability. So it converts that to Waller, W-A-L-L-E-R, Matter, M-A-T-T-E-R, road. It's meaningless. But an English speaker would know that it's not meaningful to say it one way, it is meaningful to say it another. And so it's not probability that determines my understanding, it's the word recognition and then the use of that word in a sentence. And here's perhaps the most humorous part of it. Most recognizers behave not like scientists, but like mad inventors or untrustworthy engineers. The typical recognizer gets it into his head that he can solve the problem, and again, is the problem like one simple equation, E equals mc squared, or in the case of brains, is it more complex? And obviously it's more complex. The basis for this is individual inspiration, the mad inventor source of knowledge, or acceptance of untested rules, etc., the untrustworthy engineer approach. The reason this is important is it killed AI research in those areas for 10, 20 years. And then the solution to his problem is the thing that we're still living with, which is the current benchmarks. And yeah, he goes on. It's worth reading this stuff. All of these will be in the YouTube comments or information field. To sell suckers, one uses deceit and offers glamour. So for you entrepreneurs, he's calling you somebody that's using deceit in order to get your funding. And it goes on. What was the solution to this? Well, give up. So 75 to 86, no research funding for machine translation or automatic speech recognition. Okay, so the problem with this model was that it was solved, and the solution was given by DARPA in 1985. So in the Russell and Norvig book, they're saying 87. This guy's saying 85. That's probably the right starting point. So you want to protect against glamour and deceit, and you want some sort of independent agent to help you with your tests. So we're trying to make sure simple, clear, and sure knowledge is gained, and we're avoiding glamour and deceit. So this was a project that could get US government funding, and as a result, we still have this system. Let's have a look. So in this case, you basically get data, you get the results that you have to get for that particular data, and now you're processing data sets in order to produce results, benchmark stuff. So Peircean, so the John Peirce model said you can't turn water into gasoline no matter what you measure. And then here's the conclusion, but it worked. And I used the same example when Jelinek, from when he was at IBM, said every time I fire a linguist, the quality of the speech recognizer goes up. Yes, you can win the battle, but still lose the war. And we've lost the war because today's systems are not working, not to the level that a normal person would expect them to work. It beats the benchmarks, and those benchmarks are awesome, but we're not solving the problem. So this bottom line, a self-sustaining process was started. The bottom line is it appears like we're on the right path because now it's scientific and people are improving the system. You can see here progress comes in small improvements. A change of 1% can be reason to break out the champagne. 10% in the case of Geoffrey Hinton's deep learning success against ImageNet in 2012 was reason to break out the champagne, but it's not the revolution in science. It was simply some good engineering to solve a particular problem that was annotated data and an image data set. So what's the difference between that model, which is scientific? You're doing experiments, the data's open domain, the results are published. If you get the right results, then your system's effective. The difference is that when a scientist like Galileo is looking at a scientific problem, he's chipping away at, is it maybe there's a force called gravity that's affecting things. If I do this experiment, does that either support my hypothesis or not? So that's what we're aiming to do. to constantly refine our scientific model. And the trouble is, if you're just given an experiment to do, you're doing good engineering to prove that you can beat the engineering, but you're not doing science, because what's the underlying model when somebody gives you 12 benchmark tests to pass? So you can see here, this looks like a test for gravity, depending on what the angle of the incline is, and then measuring the acceleration of the object. And obviously in the 1600s or whenever Galileo was around, the types of measurement tools that were available were quite limited. So that's the reason I say that we're not doing science; we're just doing engineering, pretending to be science. I've written an article here. Again, it's in the comments. Innovation inside the AI winter, and I reference these articles and can see a bit more detailed discussion about these models. Well, that's a good quote. We're being very kind to the software. We're only living in a very small fraction of the errors the software is making, and when you translate that from the ASR into something that's meaningful, we are only leaving in a very small fraction of the errors the software is making. Here's a modern test, superglue. And the glue tests were an early collection of benchmark tests. Superglue is a more recent collection of benchmark tests. But I'm just going to note what the limitations of this test are. It's considered a natural language understanding test, superglue. Do I have the definition of superglue here? Superglue. Nope. So there's a passage. So here's your data. Barq's is an American soft drink. Its brand of root beer is notable for having caffeine. It was created by Edward Barq and bottled since the turn of the 20th century. It's owned by the Barq family, but bottled by the Coca-Cola company. And then the question, is Barq's root beer a Pepsi product? And the answer is no. So if you give the answer no, you pass that test. How many answers can you give? Well, yes and no. So you've got a 50% chance of passing this benchmark test without knowing anything. And that's not the right way to go about tests, I would argue. Not if you're testing for language understanding. The right way to do a benchmark test like that, and I've got an article on that we'll talk about in a future episode, is you test every aspect of that. You use passive constructions. Let's see, Barq's is an American soft drink. Well, the question is, from what country is Barq's soft drink based? That type of thing. That would actually be testing that you're understanding the phrases. You'll see it in the demo in a moment. What's another one? This test, Dana Reeve, the widow of actor Christopher Reeve, has died of lung cancer at age 44, according to the Christopher Reeve Foundation. The hypothesis is Christopher Reeve had an accident. Entailment is false. So they're testing whether what you've been told entails the fact that he had an accident. A human being would be struggling with these types of tests because you know that he had an accident riding horses and was paralyzed and so forth. So that's our background knowledge coming to bear. Okay, and this is probably another interesting topic. When we're looking at where these benchmark tests come from and then who's doing very well at passing these tests, you'll notice that superglue here is sponsored by New York University, University of Washington's NLP group, Facebook's AI team, and DeepMind, so Google company or Alphabet company these days, and Samsung Research. So these benchmarks are being created by the people that need to pass benchmarks in order for their business models to work correctly. So they're not people that are trying to build a revolutionary new product based on NLU. They're people that are trying to get their phones to work better or their Facebook pages to messenger pages to do more interesting things. And at the end of this, we'll have a look at what Stanford's up to, because I think that's quite interesting when we get there. So let's go back to the presentation here. So the summary of all of that was that we've gone into this world where benchmark tests are the things that we're really focused on. Benchmark tests proceed slowly, but the goal of NLU isn't necessarily served by that, because you're not trying to pull out, well, what's the meaning of this? We're not doing what linguists do that are interested in functional linguistics, like relevant reference grammar, like Robert Van Velen. We're not looking at what is it that makes the language work. We're looking at how can we get this string of characters to produce this answer no. And they're different problems. And in fact, one of the things that you should do if you're doing benchmarks is get some independent organization who you don't financially control to do the benchmarks. And then you'll see the benchmarks fail because the benchmarkers will be really keen to make them hard enough so that you're constantly stretching your teams. Not, hey, they got 99.999% on this one. We'll tweak it a little bit so that they get 99.998 on the next one until they change one value of some parameter. Okay, distributional semantics. So what is it? For those of you in the field, you'll know that distributional semantics is encapsulated by J.R. Firth, famous linguist. I think he was English. His famous quote: "You shall know a word by the company it keeps." And on the basis of that, all of today's science, from word2vec to Elmo to BERT, all of the transformers BERT, all of those are now completely tied into science because that's what J.R. Firth said. Except he didn't. So here we go. Distributional semantics underpinning today's models. Word vectors was the original concept, and word2vec was at Google a very big breakthrough because they were able to productionize that technology. And GloVe is the Stanford product that does basically the same thing. Elmo, then we're starting to iterate on our epicycles. So I'll just give you my scientific analogy because I like doing that. So you're told that you have to model the solar system, and the planets and the sun move in circular orbits. And as you watch these retrograde motion going across the sky of planets, you go, how can that possibly make sense? And you add an epicycle, a circle, to the circular path that's being followed, and you finish up with kind of roughly the motion of the planets. What Elmo noticed at what they noticed at the Allen Institute was the word vector model that word2vec creates is giving you one vector per word. So if you've got a word that has multiple meanings, you're only getting one vector for it. So the polysemous, the multiple word senses that apply to words, is not being dealt with that model. And so we need a solution to that. Elmo was one solution, and then Google threw some resources at this, came up with a transformer model, which I would argue is an engineering model, not a scientific model. And the transformer model then looks at each of those word vectors and will assign different values to those vectors depending on the words that are in its company. So it's simply looking at word collocation. But it's not how language works. And here's a view of how language works. This is my model for the world's languages. Notice here we've got things that are language specific. So the words, the vocabulary in a language, the types of phrasing that you use in that language are very specific. You can have specific names as well, titles like The Wizard of Oz. That's a sequence of words that's unique. But you can also have words like the privileged syntactic argument comes before the first auxiliary verb, or there's lots of ways of describing it. But that's the language specific stuff in blue. And then on the other side, you've got the meaning of the words, of which there can be many. Have a look at a dictionary. There's lots, although you can simplify that considerably. And then you can go from those word senses across to the super knowledge graph. So your context representation, it's an unambiguous and without you can see the previous model that we showed. We've got the signs, which are the words and phrases in the language, the things that you can actually see. And then we've got the meanings of the signs, which in the Charles Sanders Peirce model are the interpretants. But then you've got the text of utterance, or as J.R. Firth called it, the context of situation, where the people involved in this conversation that establishes your immediate common ground, your current context, that's where that lives. So the bit on the green side, we see in search engines, if you ask for a store, it knows where you are, and it can then give you the local store. It's not the one on the other side of the world, which isn't too helpful for you. So context is being used to some degree, but if we have a look at things like BERT, they're getting access to strings of characters in big data sets. You can argue, well, it's getting some sort of meaning out of it. Well, don't buy that. There's no meaning there to be found. But we'll see how people can argue that one. So here's what Firth actually said, and here's the critique of it. Now, this is a complicated slide. Hopefully you can see that okay. This quote here is the type of thing that you'll see in an NLP book. So distributional semantics and word embeddings. The notion that semantic meaning is derived from context is the central assumption of the distributional hypothesis. As famously summarized by J.R. Firth, you shall know a word by the company it keeps. Okay, well that looks pretty convincing. J.R. Firth is the guy that's telling you that it's the company it keeps that matters. Just to clarify here, you know how I don't like the concept of NLU being what a conversational engine does when it matches an intent, because it's not understanding anything, it's simply matching word vectors together. Context doesn't mean this at all. Semantic meaning is derived from context. So if you get context, which is a document, that's not how linguists talk about context. That's simply a way of a computer scientist pretending that they're dealing with context. Because what context is above. So here's J.R. Firth's model from 57. Context of situation is a bunch of participants, right? So you're having a conversation with someone, you say certain things, you can now use pronouns in that conversation because you know that person is in your conversation. If a new person joins your conversation, you can't use the same pronouns because that person doesn't know what you're talking about. So you have to repeat things that you've said to the first person, and that's why it's annoying when people turn up late to meetings. But this is old stuff from the 50s. It depends who the participants are, what are their verbal actions, what are they saying, are they pointing at things, what else is happening, where are they? All of that is part of the context of situation. And I think in the more recent semantics books that I've pointed people to, you can see that context of situation becomes context of utterance. It's fleshed out a bit more, but the fundamentals are still there. So context of situation is important. And here's a quote from somebody else. Firth talks about linguistics with his anthropology background, and context of situation starts everything. Okay, so you've got the NLP view, which says Firth is behind context, is behind you shall know a word by the company it keeps, distributional semantics. And then you've got somebody else saying that context of situation is needed to interpret Firth. Let's see what he actually wrote. So here, this is from Firth's 57 book, the same that has context of situation in it. The meaning is dealt with at a bunch of levels: collocation, syntax, including colligation. So colligation is where you're adding noun phrases and verb phrases together and combining them. Phonology, phonetics, etc. So meaning, he's saying, is a bunch of different things acting together, not this next bit. In these examples, it's commonly collocated words with these other words, a word by the company it keeps. So in terms of collocation, you shall know a word by the company it keeps. Yeah, that's fair enough. He's not saying that this is how distributional semantics will work. And if you weren't sure about it, if you read the next paragraph, he says, from the preceding remarks, it will be seen that collocation is not to be interpreted as context, by which the whole conceptual meaning is implied. So Firth isn't the guy behind word vectors. If you want a strong example of it, we can simply have a look at this in action. So here's a public website. It's a European Union website. It's got a semantic calculator. And what you do is, I'm pretty sure it was Jeff Hinton who came out and said, the amazing part about these word vectors is you can say king is to queen as boy is to girl, and it gives you that information. And it kind of does. Some of the time, but it also has these associations, which things like bird are going to be incorporating, these very extended types of associations, where it's going to bring in all sorts of errors. And ultimately, language, I claim, is an unbelievably precise and accurate method of communication. And if you kludge in a whole lot of things that are inaccurate from the start, you can never get to the end result. And that's why the concept of adding epicycles is simply taking your currently not working model and adding a change to it to make that also not quite work, and then making more changes so that still not quite work. which is word vectors to word to vec to Elmo to Bert. We're simply adding epicycles in our science. Notice here, king is to father as queen is to what? And the looks like the first choice, queen is to mother. Okay, well, king, father, queen, mother, that's good. Grandfather, that's completely wrong. King is to father as queen is to grandfather. The probability 60%. Don't know what that means. It's a noun. King is to father as queen is to husband. Completely wrong. Stepfather, completely wrong. And stepfather is blue. What's that mean? Medium. Don't know. Medium word frequency. And grandmother, 61. So queen is to grandmother. No. So of these, yes, the first one is valid. The other ones aren't. My guess is that all of those other ones in the BERT model are going to be fed in and then distort the results that would otherwise be more accurate. Let's have a quick look. So if you go to this website, vectorsnlp.eu, you can so let's see, man is to woman as boy is to. So we've done that. Here's the response time if you enter that. Man is to woman as boy is to, I would think girl, yeah. Schoolgirl, never, because in context, schoolgirl is a more specific example, and you just wouldn't say that. Teenage, is that teenager? I think it's probably teenager, and we're missing it because of the noun at the end there. Man is to woman as boy is to woman. Women, plural. No. You can see the numbers here, 68, 58. If it's 68, do you trust it? I prefer 100%. So the difference is, as we look at this model, you're seeing some numbers with some statistics, and really it's up to the developer to decide what to use. And my guess is, if you're trying to pass a benchmark, you could tweak some of these values and say, if it's more than 62%, then I'll accept it, otherwise I'll do something else. And you might find that your benchmark results are better, but you're not solving the problem, which is, people can do this stuff. I just gave you an example where I'm talking it through. But play around with it. I was horrified, personally, when I tried to put in some values here and realized how limited it is. Having said that, this may not be the world's greatest implementation, so who knows? But it's interesting to play around with. Okay, so is that big enough for you to see? So here's the conversation engine at Pat. And let's just have a look at what it means to be using context in conversation with a couple of examples. So let's go to this one. I'm just going to run them all because you get a feel for how long it takes to run. And we've got a synthesizer running, which is a bit annoying. So you can hear it talking in the background. But now we've got help turned on here, so you're seeing, as we resolve pronouns, we're giving some debug help to see what we've just recognized. But let's go through this while it's doing that. So we've got Beth arrived. So both of those are concrete words. They're not indexes, not index signs. She saw Sam. That's the first index. So she is referring to something in our current conversation. We're not talking about Queen Elizabeth II. She has to be something in our current conversation. And so Beth would be the choice there. He kissed her. He has to refer to something in conversation. Sam, her has to refer to something in conversation. It's not she, it's Beth. And you can see here, Beth was chosen to mean she. Sam was chosen to mean he. Our debug text doesn't show the multiples. It matches her is going to be resolved correctly. The dog arrived, she walked, it. It is going to refer to the dog. And you can see then as we go through and interrogate the context being the meaning of what's been said. When you say who was walked, the dog. So we didn't say the dog was walked, we said it was walked, caused to be walked. And we get the dog was. Did Beth walk the dog? She did. So it knows that it is the dog. Who was kissed? Beth was. Was Beth kissed by Sam? Yes, she was, etc. And if we look at the current context, you can see that we're using the context very intimately. So she saw Sam, we have this variable she, and if we click on the details that we've matched, we've got Beth saw Sam. So even though the semantic representation is she saw Sam, we've resolved it to be Beth, and we've tracked the fact that she was the word that was our index into the context. And while this is working, just so you know, as we're doing the pattern matching step, we've integrated context so we can work out what makes sense at that point in time. If you try and work it out statistically, it's never worked accurately. And that's one of the problems that we have to live with. So that was she saw Sam. He kissed her has got the same type of challenge. Sam kissed Beth. So no magic's going on. We're resolving it in real time as we're coming up with the problems to solve. The dog arrived. She walked it. So you can see here she does something which causes it to move with a manner of walking. And if we look at the context here, you can see Beth walked the dog. So Beth caused the dog to walk, would be the paraphrase. And there's no magic then in the conversation because we understand everything. And then it comes back to, does our specification allow for syntax of a certain type to map correctly to this so that we can extract the answers and then give the right responses? And you can see from the rest of that example, yes, it's possible to do, and yes, it's working. So let's just do 2 more examples. I'll pick up the pace a little bit. So here we go, upload file. So this one, this is an airline example. Let's just run them all again. So Beth and John flew to London yesterday. So Beth and John is the constituent. So both of them flew. And then in language, we can use pronouns to refer to they. So both of them, or he referring to John, or she referring to Beth. If we didn't know what their gender was, we could prompt at that point. But once you've identified it, you know who you're referring to, and now your conversation can take place without error. Okay, so let's just go back here. So Beth and John flew to London yesterday. They ate a snack on a plane. So we chose Beth and John to mean they. Well, that's good. So it's the combination. And this came from Van Bellen, of course, because as a linguist, he's unsurpassed. And when he gives me an example that proves that these aren't statistically driven and there's complexity, he's right. So then she carried a briefcase on the plane. So that will be Beth. So she is referring to Beth, they is referring to Beth and John, and he is referring to John. He had his backpack, and you can see he is John in that case. It was large. We're choosing his backpack out of a snack, a briefcase, his backpack. So what's the secret here? Well, if you think of context as being something that's putting information in, and then you're looking to see what's current. In this case, we're grabbing the least recently used, the last element that was entered into into context in that class. So he had his backpack, it was large, his backpack is the thing that we're looking at. Is that the right interpretation? Well, could it mean a snack from the previous sentence? I don't think so. To me, that works properly. And the goal of NLU and the goal of scientific experimentation is do this stuff, analyze it, and if it works, then that's reinforcement for your model. So we've done a lot of examples where we're taking the last element in that class, and if there's a pronoun that's otherwise unspecified, we take that. It does seem to be how the brain is handling that, at least for English in my example. So it was large. Okay, we choose backpack. So once we've resolved that, we can ask questions and know that we're getting the right answers. Who flew to London? Beth and John did, so we're answering with a compound. What did they eat? A snack. Who carried a briefcase? Beth did. So we seem to be able to answer questions. I've got one more set of one sample to go. So let's have a look at the question. I think, Dennis, there was a question from you. Semantic calculator presents a great example of language ambiguity. So the semantic calculator that we looked at in the web vectors, is that the one you mean? I think so. So yeah, there's ambiguity in language, and this is also highlighting the ambiguity, but also the power that we've got with language, because as we're looking at these examples, you can see that there's an awful lot of information being brought to bear to solve these correctly as a person would do. And people are great at this, so let's keep emulating it. Okay, I'm going to show you my last prepared example here. Generalization. Just run them all. So Beth and John flew to London. I noticed that in the time it takes me to read that, the system's handled it, stored it, and is answering questions about it. So in this case, in our context, we've got somebody flying to London. Can I? UI. I'll see if I can fight the UI. Yeah. A complimentary meal was served. John ate a hamburger, Beth ate salmon, David ate pizza. So if you eat a hamburger, a person would know that you're eating a sandwich, because hamburgers are type of sandwich. If you're eating salmon, you're eating a type of fish. If you eat pizza, you're eating, I don't know, some sort of Italian dish. All of those are generalizations, and generalization is one of the areas that we've not handled particularly well. When I say we, deep learning doesn't handle these types of generalizations in common sense, and that's why it's an open problem in that model. If we look at the context here, you can see we've entered Beth and John flew to London. It's a type of motion with a manner of flying. We've got a complimentary meal, so that's part of a sentence, and we've got the meal being free. And then let's see, what's this one? John ate a hamburger, so we're eating a hamburger that was consumed. Beth's eating salmon, so there's a distinction between an active achievement versus an activity. These are activities because there's no specification of whether the salmon was eaten completely. Beth ate salmon and David ate pizza. So with that as our context, we can now use the generalization from the semantic model and the context model to get more information. So notice, was the food free? We give that answer, which is, I don't know, but it is. So we've got some work to do in our model where when we say a meal was complimentary, we're saying the meal is complimentary. If we ask about it in past tense, we're giving the fact that, well, it is, but we don't know if it was. I'll just prove that. So if we say, is the food free?
Is the food free?
Yeah, yes, it is. So we've just stored it that way. We need to update the conversation engine to correctly interpret when we're adding something that could be either. But notice here we've got some generalization going on. Did anyone eat? So anyone's a pronoun. Yes, they did. So we've got, let's see, John, Beth, and David eating. So someone did. Maybe they is not the right answer. Maybe we want to say something else. Who ate? John, Beth, and David. That's the generator giving us the that, and we've got different ways of expressing that. Did people eat? So the assumption is that John, Beth, and David are people. So yes, they did. Who ate what people? I would say who ate, I guess, but what people ate? John, Beth, and David. So we're extracting something at a slightly different level. Who ate a sandwich? John. Who ate fish? Beth. So Beth ate salmon. That's a type of fish. So even though it's not in your training data, in your input data, you understand it. Who ate food? So all of those things are food because you're eating it. Who ate what? John ate a hamburger, so this is multiple intents. Beth ate salmon, David ate pizza. And then, is the food free? We said it was complimentary food, so that means it's free. So you're extracting from the meaning of that sentence. Okay, so what I've shown you is that if you leverage off context, you're then able to do more than you can if you're simply working off the word forms that you're given. So all of the complexity around what else does this word mean is coming from your semantic network, and then the context network is tracking who's talking to whom in that conversation. So to me, the science being right is about taking what Roland reference grammar says the science is, which is syntax linking to semantics bidirectionally in context, considering discourse pragmatics. If we're implementing that model and we keep improving that model and we keep implementing our engineering to that model, we're going to get better and better solutions over time. Okay, so what's foundation AI? I'm saying it's investment without science. And the reason I'm saying that is because we're taking deep learning, which is a good system for passing certain tests and for doing certain types of non-human level jobs, and investing heavily in the promotion of this technology before we've actually got the science right. My example there, Newton made math exciting by showing that it solves problems, not by promoting it. He used it for things. I used it when I was at university, F equals ma, to derive planetary motion. Equations can be extremely powerful, but they have to be based on the science and they have to work. So what was the deep learning revolution? So Geoffrey Hinton's work in 2012, 10% improvement over the current ImageNet solution using a convolutional neural network. It shows that technology has got application. It doesn't show that there's a science underpinning it that we can then use for other things like NLU. It could be, probably isn't. The world of IT pivoted on that basis, and it then led to a whole lot of predictions that haven't come true because the science doesn't stack up for this particular implementation. Andrew Ng, for example, when we talk about the elimination of radiologists, so Geoffrey Hinton, I think it was in 2016, was having a good laugh at an audience where he was saying, we won't need radiologists in 5 years. They've just fallen off a cliff. They just don't realize it because they're like the roadrunner and the coyote. The coyote's about to fall to his death. Well, that wasn't true. And in fairness, the guy's not an expert in radiologists who also do diagnosis, and they can read multiple types of output. It's a very skilled job, and simply the one task of reading those radiology outputs isn't the only thing they do. So it's all about understanding. If we look at ImageNet is somebody that's marked up their corpus, their images with some descriptions, and the system's able to pull descriptions out. It's annotated data. It's not how a human would do it. When a human looks at an image, they understand what's going on. Maybe there's a bus in the scene, maybe there's a road, maybe there's some trees. You understand the scene, and based on understanding it, you can then answer a myriad of questions. So again, the challenge is if your benchmark is show me an image and choose from these 3 multiple choice answers what it is, you've got a 33% chance of getting the right answer without knowing anything. And whether or not you're getting high pass rates doesn't really matter. If you want to test this properly, show an image, ask 1,000 questions, get 100% of them right, and then you're getting towards human level understanding. You can then very quickly pick apart the things that aren't working. The same thing applies to language. Our test suite does exactly that. We'll put in a test sentence, and then we'll ask 50 ways, 100 ways of interrogating that question. Okay, so where are we at now? Look, you can read this. We've got systems that have performed at better than human level at chess and Go. Jeopardy was beaten by some very clever programming at the time. The thing is, these systems don't understand the way a person does, because you don't take that chess knowledge and apply it to some other problem. But they're very successful systems. The other areas that we're pretending are really good systems are things like machine translation. Google or Alphabet, whoever drives that in their organization, can now take multiple systems and automatically transfer information between different languages as long as they have language pairs. And it's pretty amazing it works at all, but it's not human level translation. You can't use the output of those systems for things like teaching. So there's a long way to go before you can say we've solved the problem of machine translation. And yet it's used as one of the introductory slides if you talk about deep learning. We're amazing at translation and voice recognition. Everything's done there, which it isn't. And then you can move on to, and now we're going to try some other things. Probably the biggest deep learning gap is the level 5 full automation in driverless cars, where Elon Musk has been promising that we're going to have driverless cars years ago. So I'm not being overly critical here. I'm simply saying that these are difficult problems in that the solutions aren't obvious, and people have been working on it since computers have been invented. So we've got 60 years of experience now in trying to solve some of these problems. They're not that hard to solve once you're working with a scientific basis. And in NLU, the scientific basis comes from doing the work, getting your scientific model, testing your model with your tests that validate your model, and then keep iterating on your model until you can do more and more. So here we've got Stanford. They created this group, Human-Centered AI, HAI. Very, very well-funded group. I think it's something like a $10 million per year spend. So, pretty well-funded startup, if you like. And this Foundation AI is one of their subgroups. And there's a paper here I'm just going to analyze. I think that's 100 names, but I just read that somewhere. Percy Liang is the lead of that group, I think, who's from the computer science group at Stanford. And it was formed in 2019. So we've scaled up this system based on foundation AI. Well, what is it? So it starts with machine learning. So machine learning works without context, as a linguist would call it, and meaning. Okay, so we'll start with that. We'll then go into deep learning, which is now a subset of machine learning, and then foundation models, which is a subset of that. So to me, it looks like GPT-3. Well, they mention it here. You've got GPT-3 as an example of a foundation model. So we started the discussion today with the fact that these foundation models, like the Facebook example, were taken down very quickly because it was causing problems. People assume that if you're using language that you're being truthful, and the trouble is these systems don't work that way with meaning. So they're simply taking fragments of things statistically and combining them apparently randomly. But the challenge is we don't want to do what happened in the 60s, where everybody threw their weight behind formal linguistic models to the exclusion of everything else. You have to keep researching better methods. If we simply throw all of our weight behind these big corporate inventions, we're not going to make progress for another 10, 20, 30 years. Let's have a look at one of the I say ick here, maybe I was writing a longer word, but here's the team of people in this very large paper that are writing about the philosophy of these large language models. And I'm just going to read it. Yeah, okay. I'm just going to read this and we're at the end. So the best foundation models at present can consume and produce language with striking fluency, but they invariably lapse into sort of incoherence that suggests they are merely stochastic parrots. So that's Emily Bender's work in 2021. Are these lapses evidence of inherent limitations, or might future foundation models truly come to understand the symbols they process? So firstly, they don't process symbols, as Charles Sanders Peirce would say. They're processing letter sequences. There's no meaning in there. So is it scientific to speculate on whether the future will have no inherent limitations? Well, no. I mean, if philosophically, these things are stochastic parrots. And then ultimately, we conclude that skepticism about the capacity of future models to understand natural language may be premature. Skepticism may be premature. Yeah, okay. It is by no means obvious that foundation models alone could ever achieve understanding. Yeah, that's right, because they can't. But neither do we know of definitive reasons they could not. Yes, we do. So it's hard to read that from me, because what you're saying is that I might put a cape on and I might fly around the world. We don't know definitively that I won't. I probably won't. And in this case, this is a group of 100 scientists putting their name to the fact that they're going to put capes on and fly around the world, maybe. So in summary, look, there's a scientific crisis in AI. We've moved to focus on benchmarks that gives false hope that we're achieving benefits, but we're not, if you look at what the actual goals are of this technology. I'm cautioning against being all in on the latest fad before you can get the science right. And we know that the science without meaning and context is not the right solution for NLU. Do we have questions?
I think, John, we'll ask people to continue in the commentary or the comment section after the recording is available, given that we're at the top of the hour or nearly, and there was a lot of information there for people to take in. And as I said, we'd love to see and hear the comments and questions later. And I'm sure we will. It's such an important and hot topic. It should be debated. It is debated. It's being debated in a big way with the scientific community and available on social media, which is great because everyone can see it, or nearly everyone can see that. So thank you very much for your time, people that are out there and that are viewing this as a recording. Thanks, Janice. That's great feedback. We'd appreciate to hear other feedback about how we can make these more applicable to you. I would love to see your questions and answers and more interaction in the live streams as we proceed in this new series, The Next Generation of AI. Please subscribe to the channel so that you're notified in the future of the episodes, and you'll see next week's very soon. Thanks very much, everyone. Thanks, John. Bye.